Okay, so hello everyone. Hello everyone. My name is Thitrin Sastarasadhit, or maybe you can just call me Mark. I'm from Chulalongkorn University, and today I just want to talk about my attempt at implementing a transformer model from scratch in Chapel, and also its performance compared to C++ on CPU too. Now, here's my agenda. I will tell you about the methodology first, and then I will talk about the first test that I test a small size of the model on a single thread. And the second test following is the full size model on single and multi-thread on another machine. And in the end, I will share some of my thoughts on productivity on this project. And for the fourth, second, and third section, I will also talk about like issue I encountered along the way and also the solution that I took also. And this presentation should take about 20 minutes, including the question section, which is the after my presentation. Now, first, the methodology. In this project, I compare 4 model, C++, Chapel, and 2 in Python, which use PyTorch as its backbone. The C++ and Chapel version are implemented from scratch, and they are very similar, and all variable and functions can be mapped from one to the other. While the PyTorch A, I took it from this blog, the transformer from scratch blog. I provided the link here if you want to see. And for the Python B, it's just the Python A with the transformer layer replaced with this block, transformer block from the PyTorch. Now, the reason that I include both PyTorch version is just for you to have like some existing framework to have as a reference when I compare the performance. And this project only compare on CPU only. GPU and multi-local is not included in this project. For the test environment, the 4 model were tested on 2 tests, right? The first test on machine A, and the second test on machine B. Machine B just have like more memory for me to test the full size model. If you want to see more spec, I provided in this slide. Also, I use the Chapel 2.4 because it was available at the time of this project. And for the model configuration, the first test has the small size, right? And the second test has the full size. Now, the only thing that you want to know is that full size has like more model dimensions and support more sequence lengths here. Other the number of head and number of layer is the same. For the performance measurement, I just inserted the timer at each layer and trained it on English-Italian machine translation tasks, like for multiple iteration. The dataset from the obvious book, I provided the link here. And then I run it I train it for like multiple iteration, and then I take the time of each layer and trim the fastest and slowest 10%. And then I calculated the mean and the standard deviation. Now for the first test, the small size on the machine A, I trained it for 500 iteration here. And if you want to see the code, follow by this link, and for the detailed result in this link too. And here's the first result, the result for our task. As you can see here, at this situation, Chapel is the worst here, followed by C++ and PyTorch. And for the backward pass, Chapel and C++ perform relatively the same. And for the total, in the total, the worst here is Chapel, followed by 2 versions of the PyTorch and the C++ here. Now, there's a reason behind this result. Firstly, you might thought that PyTorch might outperform the other 2 because they have like optimized linear algebra reliability. But in this case, small model, the impact hasn't shown much. But you will see this effect when I test the full size on the machine B. Now, the next thing you want to know is why the Chapel is the slowest here. Mainly because the dropout layer and the soft rack layer, which I will tell you in the next section where I talk about the problem I encountered along the way. The first thing about the implementation that I want to talk about is the metric representations. In C++, I just implement these two functions, these two class. The first one just to store the data, and the second one is just to capture the portions of the tensor when I do some like calculations. Now, however, Chapel doesn't allow me to use the reference in the class or record, so I couldn't do the same here. Another interesting choice that I made is that I used the 1D array instead of multi-dimensional array because the first time I tested the multi-dimensional array, it's got really bad performance. Now, because got no optimization when compiled, and also big overhead from these functions at one Chapel, it's just a function to get the next element. This, however, happens when you're iterating the SIP, but if you want to avoid, you can just iterating the domain instead. It also can like solve the problem. And also this problem also mentioned in the Chapel website as a performance concern too. You can follow this link to see the website. Now, as I was afraid of like performance issue that I might encounter soon after the development, so I chose the one-dimensional array design. I also test the nested array too, but is this good because it's just 1D of 1D array of 1D arrays, but it calls non-continuous array. So what the first design is still better. For the multiplications, I just use the block tiling of 64 by 64. In this case, Chapel somehow at some specific size of metric, it can do better and do worse for the other size. The compile code seems really similar to each other. So in this case, I'm not sure why. And for the metric operation, in this case, I'm talking about the element-wise addition, multiplications, division, or something like that. The reason that I have to implement this function and not use the built-in operator is just I want to have like control over the parallelism when I do the multi-thread. If I use the built-in operator, it will force me to use all the available threads, which might or may not consume the performance when the memory bandwidth is an issue. Now, it shouldn't have no problem, but I found that the design mattered a lot than I expected. Now, I will present you 4 designs that I test. The first one, I just query the domain from the array. And the second one, I pass the domain separately. The third one, I just pass the start point and end point that I want to iterate. And the last one, I just use the reduction operator. Now, the results is unexpected. The only performance difference that should be seen is just the overhead of passing argument. But it turns out that the first one is the worst with no optimization. The second one is the second with just loop unrolling. And the third one is the best with the vector lines included. Now, the fourth one is just like the first one, but it also creates a task when I call it. Now, I have to know that it's kind of hard to produce. When I test these functions outside the model, it's also got the optimization normally. And so in the end, I end up use the third design, even it caused some like messy code or something. I also have tried to overloading operator too, but it just gives the same performance as the first one. The softmax layer. This is one of the layer that caused the Chapel to a bit slower than C++ here. It's just because Chapel refused to use the vectorized exponential function that implemented in the GeneUC library. This function can be accessed by the C++ by just pass the argument to the CLang like this here. However, Chapel refused to use it. I have tried several attempts with different methods here. try iterating the domain, try iterating the elements also, but still I couldn't make it to use this function. Now, from which I understand, Chapel use LLVM and or maybe C++ as its backend. So I think it should be able to get this function, get the access. Now, if it's not, it would be great if this is implemented to accelerate it to the exponential calculation. The dropout layer, I use the random stream in the random module which is part of the main module of Chapel. And also I use the integer random too, but still it's quite slow. The main slowness of this layer comes from the random number generator. It's quite slow, which I couldn't make it faster in this point. For the multi-head attention layer, the issue in this layer is quite mysterious. In the backward pass, when I do some like gradient of the query, the value, and the key, and also the gradient for the next layer, I found that it's quite slow than I expected. So I inspect the compiler generated code, and I found a heavily loop rolling like 20 times with no vectorization. Now it's quite interesting because other part with the calling metric modifications here got the optimization normally, but this doesn't. Didn't. Moreover, I have tried like comment out the independent code and test individually, but they got the optimization normally. So it's quite mysterious here. Now, the fix is even weirder. I have to tell you that I have a config file in Chapel to specify the parameter that is known as compile time, like model dimensions or maybe the sequence length. So for that reason, I use the param to declare this variable. However, when I try play with this by changing the param to var, the issue in this in the layer multi-thread extension I mentioned before disappeared for some reason. I still confused by the results, but luckily this change didn't affect the other layers. And for the layer, I just have the issue in the backward pass here. I have to separate the operation here to this two separate operation. Maybe it because in the first attempt it got no optimization. It could be due to the unsureness of the compiler that it has the possibility of overlapping arrays, so vectorize didn't take place. But still, I thought that this could be checked in runtime too. So I'm not sure about the result of the course here. And the another thing is in the forward pass of the review, the compiler in Chapel chose to generate these two instructions by separating the load and max, while in C++ it chose to combine them. With this, Chapel ended up to be a little bit quite faster when I tested the small model, but much worse when I test the full size model. I don't know. I'm not sure why this happened, but you will see this effect too in the layer norm. Now for the other layers, it's work fine, especially the parameter updating that I use the Adam optimization. C++ and Chapel do much faster than the PyTorch. And for the second test, the full size model on the single thread and multi-thread, which I test on the machine B. The experiment is done the same way, but I run 40 iteration in this experiment. For C++, I use OpenMP to enable multi-thread, and for Chapel, I just use the language feature like for all and for all and custom iterators. And for the algorithm and degree parallelism, it's the same between two. And if you want to see the code, here. I provided the link here and also the detailed result here too. And here's the result, the forward pass. At this situation, Chapel managed to be a little bit faster than C++ because it had a faster linear layer, but still suffer from the dropout layer here. As you can see, the gray area, that's quite big. And for the backward pass, Chapel just like relatively almost the same with a little bit faster than C++ in this case because it have faster linear layer. And for the reason that it has faster linear layer is just because better at metric multiplication at that specific side I mentioned before. Overall, Chapel win simplified by a little bit, and if also you might not be able to see here, but the LELU layer and the layer norm here is quite observable. Quite slow than C++. The issue that when I enable the multi-thread only lie in the software, because in this layer I need a buffer to store a compute exponential value for the reuse. In C++, I just declare the array in the loop. However, Chapel, I cannot do the same here because unlike C++ that doing this in the loop, we declare the array in the stack memory. Chapel will allocate and deallocate every iteration which cause a bit of performance. So I had to move the buffer out of the loop. So I think it would be great if somehow, if we can like declare array explicitly. For the other layer work fine. Some calculation that Chapel is slower than C++ in single thread. It came to be similar because I think it's because it got the memory bandwidth as a bottleneck now. Now for the parameter mapping that is already good in the single thread, it's even better in the multi-thread. Talking about productivity, I can share some of my thoughts on this when I work in this project. Now, I like that it's easy to learn because it's just like Python. I can migrate from the Python. And also it's very simple to do parallelism, parallel programming using for loop. I also like that the language require type declaration. And for the memory, I also like the memory management of the object and also within across the multi-thread too. And also I think programming multi-local is quite easier. However, some drawback I also noticed that it quite compiles, the compilation time is quite long, especially when you do the multi-locals. And another drawback that I think is that all the performance issue that I mentioned in this slide. Another thing is that downcasting between number type, like from Rails 64 to Rails 32. However, this is just a personal thought. I just like it when it do automatically. Another thing that I think it affect a lot on productivity is that generative AI couldn't support much. It might be because there's less code of Chapel on the internet for the AI to train. So it isn't good and also provide a faulty code. It would be great if this AI could do like provide can write some test code or maybe some small code that I don't have to write. Also, but I want to mention that there is a Chapel blog that do some like experiment on this also, which got quite a good result. So you might want to have a look too. I have to know that the issue that the performance issue, I didn't contact the Chapel community when I developed this project. However, I plan to do it after try to do it soon after this presentation. And for the conclusion, to wrap up this project, I illustrate the attempt at implementing transformer model in Chapel and compare performance with C++. and also have like existing framework like PyTorch as reference. The result is reasonable and also outperforms some part of the C++ too. However, many performance issues still encountered along the way and need some like tricky solution. Additionally, some feature like having a reference declarable in the class of the code could be added to get the language better, or maybe a faster compile time. Also, this project didn't demonstrate the model on GPU and also on the multi-local because like time limit and also my capability. So it would be great if this was investigated. I also have to say that this is my first Chapel project and also my like first performance experiment at this scale. So I did this project back in July when I was an intern at the University of Tokyo in Professor Kenjiro Taura lab. The code itself is probably not the best and many improvements could be done. I'm looking forward to study in this high-performance computing field. So if you have any suggestion, advice, or comment, anything, you can just contact me through this email. And thank you very much for your attention. If you have any question, you can feel free to ask.
Let's thank the speaker with a virtual round of applause. Thank you very much for the talk. So we are actually now at the break time. So officially we will have the break until XX00, so until the next hour starts. But if you have questions for the speaker, feel free to ask in the chat. So see you back in 15 minutes.
Hey, Thitrin, can I ask a couple of questions?
Yes.
Yeah, sure.
You showed some functions that went by too fast for me. Plus reduce, I believe. Like there were like 4 versions that you implemented. They are doing the same thing seemingly, but optimization behavior was different. Is there any chance could you flip back to those slides? I didn't make a note of the slide number, but I hope that you remember. No, there were like 4 different implementations of the same function, plus reduce, I believe, that you wrote yourself to have more control.
See. Just
These ones, yes. What was the fastest version? I think it was in the next slide, plus reduce 3.
The fastest version is this one, the third one.
I see. That's interesting. Yeah, I think it would be really